All right, Rolle's theorem and the mean value theorem today. Rolle's theorem was named after a French mathematician. He lived from 1652 to 1719. And it gives conditions that the guarantee of the existence of an extreme value in the interior of a closed interval. Meaning, if I have a closed interval of a smooth and continuous curve, that I'm going to have at least one, either in a maximum or a minimum, when you have a smooth and continuous curve. I don't have to have both, but I have to have at least one of the two. Okay, so I'm kind of trying to draw a picture here to show you that. All right, so both of these are closed intervals. This one happens to have a relative max. This is actually an absolute min, and there's an absolute max. If I take a look at this next one, see, I do have an absolute max there and an absolute min. So again, that's what it's basically talking about, is that if you have a smooth and continuous curve, and then you're going to have extreme value. You're going to have at least one extreme value in the interior of the closed interval, unless it happens to be a constant function, which is just a horizontal line. So if I have two endpoints to a graph and it's smooth and continuous, we have to have at least a max or a min between the two endpoints. So what happens with the Rolle's theorem, it says if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, provided that the value of f of a equals the value of f of b, that means the y-coordinates. If those are equal, then there has to be at least one number c in the interval from a to b such that the derivative is equal to 0. And this one, if the differentiability requirement is dropped from Rolle's theorem, then f here would still have a critical number in the interval from a to b, but it may not yield a horizontal tangent line. So understand, tangent lines cannot occur at a sharp point like this. So this one here would not yield a horizontal tangent line. It says find two x-intercepts of this function. Show that the derivative of f of x at equals 0 at some point between the two x-intercepts. So first we need to find the x-intercepts. That means we're going to take the equation equal to 0. So once I took the equation equal to 0 and factored it, here's what I got. I get x equals 1 and x equals 2. So what that's telling me is that f of 1 equals 0, f of 2 equals 0. That means there exists some number between 1 and 2 such that the derivative is equal to 0. Well, think about that. It's a parabola. This parabola opens up. I just told you this parabola crosses on the x-axis at positive 1 and positive 2. So doesn't the minimum have to occur somewhere between the 1 and 2 on this parabola since that opens up? And I hope that's what you were understanding there. All right, so if I went ahead and took my derivative of the function is 2x minus 3. Set that equal to 0 to get my critical value. So therefore then, that would make x equals 3/2. See, here's the graph. The original function, the x-intercepts at 1 and at 2, and notice my vertex was at x equals 3/2. So Rolle's theorem can be used to prove another theorem called a mean value theorem. If f is continuous on a closed interval from a to b, then, and differentiable on that open interval, then we're telling you that there exists some number c in that interval, in that open interval, such that the slope at some point c would equal the slope of the endpoints of the graph. So let me go ahead and give you guys a picture of that theorem. Let me back that slide up. Okay. So basically, here's what's happening. I'm drawing a picture real quick, and I will show you it here in just a second. Okay, so the red graph is the curve. The line would be the slope between the endpoints, if I said a closed interval. So my graph is smooth and continuous over all real numbers, actually. But it said f had to be continuous on a closed interval from a to b. So I'm closing it off from this point to this point. And it's definitely smooth and continuous. It's differentiable, no sharp points. So what they're telling me then is that there exists somewhere on this curve right here will equal the slope of this line that I just drew between these two endpoints. And that's what the mean value theorem is telling you. Okay, so there exists a value somewhere between them such that the slope of the curve will equal the slope between those two endpoints. And that's the mean value theorem. So it says, given that f of x equals 5 minus 4 over x for all values c in the open interval from 1 to 4, such that Now, I'm told that f of c is to equal f of 4 minus f of 1 over 4 minus 1. Now, first off, this domain, y'all, x can never be 0. 0 is not in that interval, so I'm okay with to continue then. So plugging in f of 4 right here, 4 f of 4, so 4 divided by 4 is 1. 5 minus the 1 gave me 4 here. Then plugging in 1, so 5 minus 4 divided by 1, that gave me 1. The denominator would be just the 4 minus 1 from here, which happens to be a slope of 1. So this is telling me that somewhere between x equals 1 and x equals 4, there has to exist a point C on the curve such that the slope is equal to 1. That means that I need to take the derivative of the function and set it equal to the slope that we just found. So we take the derivative of the function, set this equal to 1. Well, that's going to happen when x is 2 or negative 2. If I go back to the original, the interval was from 1 to 4. Negative 2 is not in that interval, so I would only keep the x is 2 as my concluding answer. Now this is a picture of what that looked like. So again, here's the picture of the curve in black from x equals 1 to x equals 4. What we found first was the slope of the line for this endpoint right here. So the slope of that line happened to be 1. It's the second y minus the first y over the second x minus the first x. That's all that is. Then, because this was smooth and continuous, no holes, no jumps, no breaks, no sharp points, we went ahead and took our derivative, set our derivative equal to the slope of that secant line right there. Because we're trying to find when on this curve will the slope of that curve equal the slope somewhere between these 2 points. And that happened to be when x equaled 2, and that right there is where the slope is, also 1 as well. So the Rolle's theorem, f of a and f of b had to be the equal y values. So Rolle's theorem, again, on your function, f of a has to equal the f of b, so that when you take the slope between those two endpoints, when those are equal, see that slope would be 0. So we're saying somewhere exists between them, there has to be somewhere with a slope of 0, like for instance right there. The mean value theorem is telling me that when I have that endpoints, that the slope between the two endpoints has to equal somewhere on here equal to the slope on the curve itself. And that's your two theorems for 3.2. Have a great night, guys.